Okay, welcome back. Spectra is basically the same rules as everything else. So there's no need to have special cases here. It has allowed electronic transitions. I guess compared to what we'd be doing before, we have another label here. I have this GU label on the bottom, and that's because if you have two atoms the same, you have an extra symmetry to do with comparing two atoms. So we actually had the same on the C2, but we didn't set C2 in any detail. And so we have an extra selection rule. It basically says you have to change G2. Essentially, this is like Jeffries. When I complained about Wikipedia, as long cheetah sits on the GU and nothing else. Whereas actually there's a item that calls irrelevance whether you will have like semi data involved. So given that, if we started the sigma G ground state, the Z impends the trip the sigma U, then it make associative. That's sort of spin the middle transition. We can go to the singlet sigma U plus, because that's sigma to sigma, but singlet, that's the GU. And that band is called the Lyman band. It was slightly unfortunate because that's the same name as Lyman alpha. It's not the same system. So Lyman in H2 and Lyman in H. And they're vectors and Lyman. And then you can go to a bunch of bats here. Some triplet pi U, that's spins are hidden. Singlet pi U is allowed. That's the third command. We need to get two bands here, which lie at relatively short wavelength, so 100 and 110 nanometers. And that means that actually there's not much in terms of space emissions that destructive observers in K1. But they are there and they are important. So you have going now to delete my writing for the one west because and that makes you choose that. So you have a situation for hydrogen like this, the rotations lying far to the right, so it can be attributed to put C to the ground. The vibration rotations lie in the mid to near infrared, and the electron inspection via the UV. So all of these actually have difficulties with observations, but for keeping H2 hatch is pretty difficult. And certain things like interstellar planets, people often use CO as a toxic for H2. They say as much CO molecule for every 10 to the 4 of H2 molecules for it to observe the CO every now and then touch H2. There's that. Not a wonderfully good approximation, but needs must. Okay, so I think that was all I wanted to say about electronic spectra. I've got some random spectra here. Shall we disappear? I haven't just skipped over that. That's actually a rotational spectrum. So it's a stellar spectrum with lives assigned in the CDNS and JKL database. And various things here. One is the complex molecules you're looking at. If you look at them, you've got molecules here with 1, 2, 3, 4, 5, 8 atoms in. And then you've got a whole lot of numes. Lots of lines. Now, this is a meteor slide, so they may not all be used anymore. There certainly are used them around. So 37 identified features and 36 are identified. 6 lines behind 100 kilometers seconds, strange units, but you can see this is a small brand. It's 231200 to 231800. So it's just a very small bits. And I thought, that's so. Now, so how do you run your FedEx? Weeks up. So instead, spend the next something I was going to do was violence. So I got we started doing the tutorials, and I think we might spend slightly longer today doing tutorials, things, and actually, that's how I stop it. If you have problems you would like me to do a tutorial question on, and remember you've got an exam tomorrow, ping me an email. So my email is what's intuitive. Yeah, that's true. Tennyson, UCL.ac.uk. So if you can email me this side of lunch on any topic you'd like me to just a bit on examples on, I'll see if I can find something for the tutorial session or something. And I've got one on hydrogen. So my electronic spectrum example of the hydrogen electronic spectrums. And I'll do that some work in something this afternoon. But I partially got wing doing other ones. I already had one thought, at least, maybe two thoughts, some examples of stuff I could do, so it'll be useful. Quite happy to be guided. Because I just think needs doing. Okay, so the last topic I want to go through was line profiles, which we've touched on occasionally already. We've worried about line profiles. And basically there are various effects on the lines. The first is natural broadening, and that is also a consequence of the Heisenberg uncertainty principle, because excited states all have a finite lifetime. And having just turned off my pen, I'm going to turn it on again. So you get an uncertainty between the energy of the lifetime or the time. So you have a finite lifetime, you must therefore have also an uncertainty in the energy. So you get a line width. Now, if the lifetime is just given by radiative decay, that tends to be such that you get no uncertainty, no real, unless you're doing an incredibly high resolution spectrum, it doesn't affect the line width. You do get cases where you get very short lifetimes because of something called predissociation, where basically the molecule tunnels out and escapes, and then you get lifetime effects. But we're not going to deal with that in this course. So effectively, we ignore natural broadening normally, except for a few very strange cases. Then the second effect is Doppler broadening, and that's just thermal motion. It's because if you have a temperature, the atoms or the molecules are just moving around and colliding with other atoms and molecules and not stationary. So that's different from a Doppler shift. So if a target viewed from Earth is moving relative to Earth, you get a shift of all the lines in that target just because of the Doppler effect. But on top of that, if there's a temperature within the target, you'll get the atoms and molecules within that will also be moving around. So they won't all shift at exactly the same velocity, and you get a broadening due to the thermal motion. That's a Gaussian. It depends in a simple way on temperature. It depends in a simple way on the mass of the species you're looking at, and it depends on the frequency. So I haven't written it down there. I may have it on the later slide. And it's very easy to calculate. So if all you have is Doppler broadening, your line broadening studies are simple. Pressure broadening is a whole different effect. So pressure broadening is caused by the fact that if you're in an atmosphere, in the time it takes to do a transition, you may collide with another species in the atmosphere, and that broadens, that shifts where the line is, because effectively you change the potential by having, so if your Earth atmosphere, maybe you have a water molecule, it collides with nitrogen while it's absorbing the light, that would slightly shift the potential surface for water, causing the line to broaden due to that collision.
And that's a pressure-dependent effect. If you have a fixed concentration of water and you change the amount of nitrogen, it just goes linearly with the amount of nitrogen in the atmosphere. So at Earth atmosphere pressures, it's important. Solar atmospheres, which I said were 10 to the minus 5, Earth atmosphere is not important. But it is important in quite a lot of things. It's normally modeled as a Lorentzian. That's an approximation. The Doppler is not an approximation. The Gaussian's the Doppler is if you assume just random thermal motions, the Gaussian is correct. Lorentzian is a model. It's quite accurate in the middle region, but there's a whole debate what the far wing should look like, and it's not a known problem. It's known, for instance, for water, if you stand Lorentzian, the far wings are underestimated. For an awful lot of other molecules, they seem to be overestimated. But actually what the correct functional form is and what the exact physical process is in the far wings seems to be a subject of debate. So obviously, if you use you have a pure Gaussian, that's easier. If you have a pure Lorentzian, that's easy. But normally you have both. So you have to take the admixture. And the admixture, or the convolution, is something called a Voigt profile, after a German scientist who did a convolution of a Lorentzian and a Gaussian, but I think it was nothing to do with pressure broadening of spectral lines. He just did it for a different reason. And unfortunately, it's not an analytic function. So it then becomes expensive to evaluate. So there's a whole litany of different approximate methods for evaluating it I won't get into, but it's a Voigt profile. But then that is making assumptions about the collisions, and you get things to do with speed dependence of the collision, hard and soft collisions, correlations, etc. So you get all sorts of subtle effects you may want to put in. And that has bred a very large number of beyond Voigt models, all of which had excruciating acronyms, completely unmemorable even to the people who used them. So I, a dozen years ago, chaired a task group with the idea of actually recommending one beyond Voigt profile, because frankly, having 8 different profiles is completely useless for people who want to do radiative transfer codes, because they're not going to program 8 different profiles, and they need all their data in a consistent form to put in the code. So it was agreed in the end that we'd use something which had an excruciating acronym, and I can't even remember what it was. So I also got them to agree that we would name it after the 2 scientists who'd invented it, so Hartmann and Tran. So they're Hartmann-Tran profiles. And the big advantage of Hartmann-Tran profile is that it's essentially a double Voigt. So computing it costs twice as much as a Voigt, whereas all the other ones cost way more. So actually for astronomy, you don't need this. Maybe for planetary science, you get accurate enough that you need it, and you need it for Earth atmosphere. In Earth atmosphere, if you use a Voigt profile, you get and you do the residue, you get a very characteristic W feature wherever there's a strong line, because the Voigt profile is not quite accurate enough. But we don't see outside the solar system, we don't see things with enough accuracy for that to matter. So not at the moment, but probably coming. So to go through that with a bit more detail, that's the difference between, sorry, I keep on forgetting that I have to do this. Magically, I get that. So that's the difference between the 2 profiles. So the Doppler is Gaussian, Lorentzian, the pressure is Lorentzian, and in particular to be noted, Lorentzian has much wider wings. So if you're in a pressure atmosphere, your line can spread much further than if you're just getting a temperature effect, because the Doppler spares off with the square of the exponential of the square of the distance. The Lorentzian just goes off with the linear distance. So you have a spectral line, obviously have a line position. I've subtracted that out of that and called it 0. And then you have a line intensity. And one important thing about all these profiles is that if you integrate over all of them, the line intensity is conserved. So that I calculate, well, I've talked about Einstein coefficients, that gives you the intensity. I do that with no Doppler effect, no pressure broadening effect, But when we put that profile on, it just spreads that intensity out. It doesn't change the intensity. So when you integrate and the area of either those curves or the Voigt profile together, you end up with the same intensity. So that gives you the line shape as a convolution of them. And as I say, the Voigt is a convolution of the Gaussian and the Lorentzian. And it's particularly important for optical thickness, because if it's optically thick, then you don't anymore get this property that the intensity is conserved because you've cut off the top. So if you had something which is optically thick, and then you increase the pressure, you broaden the wings out, you see more of the line. So effectively the line intensity goes up if you increase the pressure, even having said that the intensity is conserved. So that's just a visual image of line profiles with Doppler broadening. I'm not quite sure why the temperature at 0 Kelvin still has a finite width. That must be a natural lifetime, because the Doppler width at 0 Kelvin will be 0. That must be a natural lifetime, and then it spreads out as you go up in temperature. That's not very good picture, showing you a convolution of a Lorentzian and a Voigt. So the Lorentzian is the top curve, the Voigt is the middle one. So it has the characteristic of the Lorentzian at large distances, has the characteristic of the Doppler at small distances, and it's intermediate. So that's the sort of summary of the line profiles. So general principles of pressure broadening is that it depends on long-range interactions, because basically you're talking about things colliding. So whether you have a dipole or not in either the collider or the active molecule, you have dipoles in both of them, you get stronger long-range interactions. So water, for instance, has the 5 times the pressure broad. So the variable that's used to characterize pressure broadening is gamma. So gamma is a function of temperature, and it's a function of the 2 broadeners, and then it's a function of every single line you look at. And gamma for water is typically 5 times water is typically 5 times water-air, for example. Hydrogen, which is of course extremely important astronomically, is a very inefficient pressure broadener, as is helium, for 2 reasons. Firstly, they don't have any strong long-range moments. So leading one in hydrogen is a quadrupole. Helium doesn't even have that. And they're both very light. So the other effect you get in pressure broadening is you can just think of it as a hard collision. If you have something heavy and it bangs into you, that makes a big effect. So something like SF6 or xenon are also big broadeners just because they're heavy, where helium isn't a big broadener. So it's structurally like xenon, it's light. So line broadening decreases as temperature goes up. If you go very low temperature, 40 Kelvin or less, you need to treat it quantum mechanically. Most people do semi-classical models. Bobby's now gone, but that was what he was doing as his postdoc with Bob Gamache, was solving semi-classical models for room temperature molecules. Has a rather characteristic shape. I was going to draw it, but actually you'll see, I'll show you pictures, if not in this lecture, a later lecture, showing that they peak at low J and then they go off to some J maximum. They get flat at high J. Depends much more strongly on the rotational state than the vibrational state. In fact, it's a common approximation to say they don't depend on the vibrational state. It's not a bad approximation, but it's also made quite often out of necessity, because there is not enough data to characterize all the vibrational states, all the lines for all the vibrational states. So people just assume it doesn't depend on vibrational state, but it's sort of true. Hydrogen and helium are inefficient broadeners. I already said why, because they're light and they don't have long-range effects. And someone asked me about pressure shifts yesterday, and indeed there are pressure shifts, but they're relatively small. And that, though I promised to provide them with Exomol, we haven't, and no one has ever asked me for them. So as long as no one ever asks me for them, I don't have to make them. And I'd be quite happy not to, because it's quite difficult. So this gives just an idea of line broadening values for water with hydrogen and helium. And you can see helium is an even more inefficient broadener than hydrogen. And it's not just mass, because helium is twice as heavy as hydrogen. This is also the fact that hydrogen has a quadrupole. Cluster, I've only plotted on J. The cluster is to do with, actually, if you remember, water has all these different levels, with J has 2J plus 1 separate levels. And actually, there's quite a strong dependence. There's a stronger dependence on Ka and Kc than there is on vibrational state. So you have to account for that. But you can see that low J, got a value, and you seem to come to some, I have to say, we pretty much assumed here you come to some J value where it's constant, but that does seem to be the general effect. So if you look just specifically at our XML project, I don't know why on those things you're missing the left-hand side of the pictures, but anyway, it's full on here. We have a problem here. We have approximately 10 trillion transitions. And in principle, every one of those has a different line broadening profile for every single collider we want. And probably there are about a dozen colliders we're interested in. So obviously hydrogen, helium, CO, CO2, nitrogen, oxygen, a few more that we need to, water we need to think about, and we need to worry about high temperatures. So there's a real problem on how to solve this to get enough data. So essentially we explored 3 methods. Method 1, which is published paper by my postdoc, Andrei Sokolov, looked at using high-class first principles type methods, actually doing electronic structure calculations to get potentials, and then doing molecular dynamics, so that's classical dynamics to look at the line broadening effect. And that took him 3 years to do for acetylene for 3 different broadeners. We have 12 broadeners and nearly 100 molecules, so you can do the maths yourself. It's not very practical to have 1 man-year per person, per broadener per molecule. We're never going to finish at that rate. Gianna Buldareva had some very approximate methods for doing it, which were easy to use, gave us baseline numbers very quickly. And then my PhD student, Elizabeth Guest, we said, right, we can machine learn these. So we did a machine learning project. And spoiler alert, the results of this are better than the results of this. They're probably not as good as results of this, but the machine learning really worked quite nicely. So obviously, if you're going to machine learn, you need some data. Do you want the last slide you take a picture of? Or was it that one? Do you want to go back? Okay. If you're going to machine learn, you need some data. And the HyTran database, which, as I've said already, is an Earth atmosphere database, 50 years old, has, well, we use HyTran 2000, that had 52 molecules in it. HyTran insists that every line has a line broadening profile. It doesn't mean it's reliable. So one thing Elizabeth did actually a very thorough job on was cleaning the data. She threw out the lines which just said guess, and that's quite a lot of them. She also discovered quite a lot of inconsistencies in the data. So if you go to the HyTran website, there's a little thank you to Elizabeth Guest for correcting the following data in the HyTran database. And she's earned herself a co-authorship on the just submitted HyTran 2024 paper. And there was a period, I don't know if anyone follows these things, but Clarivate, who do the Web of Science citation alerts and impact factors and everything, published a list of world-leading scientists on the basis of how many citations anyone got. And to be a world-leading scientist, you just needed to be on 3 HyTran papers because it gets so well cited. So being put on the HyTran paper is quite important. So we used HyTran data. Hytran actually only gates data for two, at least routinely collects data for two. I'm going to use the word molecules very loosely. The first molecule is one called air. And to Hytran, air is 78% nitrogen, 21% oxygen, and 1% nothing when it should be argon. And then self, and self is obviously whatever it is, and self-broadening has a slightly different characteristic because you can have resonances. So if you're vibrationally excited in one, you can swap the energies, so it's has a different behavior. So we learned of air broadening. They are increasingly putting other molecules in, and we're currently doing another machine learning problem with trying to. So what we did was we learned everything for air, all the different possible molecules you could broaden. Now we're trying to do it the other way around. We've got all the molecules, we want to learn all the broadeners. And that takes way more data. And Hytran has some of that data, but we've got to scrape the other data from the literature. There's a problem above about 3 atmospheres. I mentioned that already, I think, yesterday when we started talking about pressure broadening. All these pressure broadening models exist on the idea that you're talking about binary collisions, 2 particles colliding. But if you get a strong atmosphere, that is no longer a good assumption. And brown dwarfs can quite often be more than 3 atmospheres pressure on the top of their atmosphere. And then I think current line broadening models really don't work. However, there's no other models, so people still use them. But you have to be aware that they're not good. So I've got more about the pressure broadening, which I think I'll start this afternoon. I've got quite a long talk on my own work, because I've got 2 aspects to it. One is the observational stuff, which I don't do, and then actually on the project itself. And I'll give you the machine learning results then. So a slide we can contemplate. I think I already mentioned what may be going on here. But this is CS molecule. Very unhelpfully, it doesn't tell you anything about the position of it because it's just in these funny kilometers per second units, which means that these are shifts relative to wherever the lab line is. But what you can see is they're all at 8.5 kilometers per second center, so it's all the same object. But I'll tell you, this is a pure rotational transition at long wavelength. And you've got a J2 to 1, J3 to 2, and J5 to 4 line. And what you can see is they've got incredibly different profiles. This is nothing to do with isotopes. Anyone got any idea what might be going on here? So if you remember, if you observe from the ground, I said you have a column and you see everything in the column. So if you have something which is hot in the middle but expanding outwards, it gets colder as you go out. So you have your central object, your central object here, and then you're expanding. And you emit in the middle, but then you go out, you get colder lines that reabsorb. But if you're hot enough in your original emission, there's nothing to reabsorb, so there's no J equals 4, there's no J equals 4 as you go out, you can't reabsorb the line. But if there's a J equals 2 as you go out, you can reabsorb the photon. But the Doppler profile for the cold lines is smaller than the Doppler profile for the hot lines. So the hot thing has a Doppler profile looking like this. The cold lines have a Doppler profile looking like this. So what you see is something which is actually the difference between 2 Doppler profiles according to the emission and the absorption. People understand that? So the original Doppler profile for the hot here is quite broad. And then you get cold lines which absorb with a narrow Doppler profile, and the net thing is something looking like that with the absorption in the middle. You can get similar things where you see things expand. If there's a really explosive expansion, you quite often get shapes looking like that. So that you've got an object here which is expanding in two directions. And so this is not a Doppler profile, this is a Doppler shift. And you get a Doppler shift going in two directions. And that's actually why people do it in kilometers per second, because that tells you immediately how fast it's going when you see something like that. So you get actually quite a lot of information from lone profiles beyond just the data I was talking about. Okay, how are we doing for time? Because that was all I wanted to say on line profiles. Okay. What I will do is I'll start the stuff on observing exoplanets, and then this afternoon, as I say, we'll spend extra time on tutorial type stuff. So I have an extended, you might call it a revision class or a extended tutorial session this afternoon prepare you for the exam tomorrow. Okay. So do email me if you want to know anything about that. Okay, so this last section, which is not in my book, is focused on spectroscopy of exoplanets. To be honest, if I wrote a 4th edition of my book, I'd probably do the first part of it. Sorry, thank you. Talking to a slide you can't see. There we go. If I wrote a new edition of the book, which I will do at one point, I'd put it. The publishers always want one more chapter on when you do a new edition. So I do it, actually, this is what I do it on spectroscopy of exoplanets. So what I'll do now before the lunch break is talk about not my work, but observational work on how you get the spectroscopy of exoplanets. And if you think about it, we can't see exoplanets, and we're taking a spectrum of them. That already is quite a mind-blowing thought, and it takes considerable ingenuity by the astronomers to do this. So that's what I'll talk about, and then tomorrow I'll talk about my own project, Hexamol. So they're all in one combined thing, but I'll talk now just about the exoplanet stuff. So as you know, this is the last of the 5 phases in the course. And actually, just to warm you up or cool you down, as the case may be, you've got the nice snow in the background there. That's Mauna Kea in Hawaii. This is actually my H3+ spectrum I'm about to show you. And that is the IRTF, Infrared Telescope Facility, made out of melted down Japanese battleship. I joke not. They scuttled the Japanese fleet in Pearl Harbor, and then they hauled it out and melted it down and made telescopes out of it. And that's the Keck telescope. Keck was a philanthropist, and they built a telescope, and he was so impressed with it, he made it a pair of binoculars. So it's 2 telescopes you can use together, which is slightly strange backing because the H3+ story actually used a different telescope, the Canadian Hawaii telescope, which is physically somewhere a bit along there on the mountain. This is an amazing observing site. You're 5,000 meters up. I think I said to you already, Hawaii, Hilo, which is a local town, is one of the wettest places on Earth. But you get a complete temperature inversion. You're literally standing there with the clouds a mile below your feet. And it's raining like anything in Hilo, and you can see all the stars, and you can see the sea as well, because it's just an island in Hawaii. So it's a very, there are no plants up there, completely dry. You go down a little bit and you get strange things. Anyone read a book called Day of the Triffids? Science fiction book? No, it's quite old. Yes, I've got a nod over there. You get plants which look exactly like triffids growing there, but nothing else. And I think I said to you that we identified this H3 plus spectrum. And my then postdoc, who was a guy called Steve Miller, who like me was a chemist in background, decided that he wanted to become an astronomer full time. And he's older than me, he's now retired. But he became a professor of planetary astronomy and he never looked at another molecule. He looked at H3 plus his entire career. But he did things like had papers in Nature on wind speeds in Jupiter by looking at Doppler shifts in the H3 plus spectrum. He showed that exoplanets, you're probably aware that the first class of exoplanets observed were hot Jupiter planets orbiting very near stars, inside Mercury orbits of stars. Why they don't just evaporate. H3 plus provides the cooling for them to radiate the data away. So he has a paper in Nature on that. When they get hot enough, the H3 plus dissociates, then they evaporate. So he used this in all sorts of very imaginative way. We had a project, and I already told you about the difficulty of forming small stars in the early universe. We had a project which was always called Steve's Nobel Prize project, because we figured if we cracked it, Steve would get a Nobel Prize. Why only Steve would, and not me and the postdoc? We won't go into. And that was actually to use H3 plus as a way to cool down enough to form early stars in the early universe, but we could never form enough H3 plus. So anyway, if you're interested in this, his sort of retirement thing was to write a 30-year review of H3 plus astronomy and reviews in modern physics. So there's a very comprehensive article there. And they're all sorts, so interstellar medium H3 plus spectra have demonstrated. So Takeshi Oka, who was the man who first saw H3 plus in the lab and spent a lot of time looking for it in space and was very annoyed when we found it in Jupiter when he was looking in the interstellar medium. But he did eventually find it in the interstellar medium. And it's there, it's caused by cosmic ray ionization. And he concluded that the assumption that cosmic ray ionization rate was the same right across the galaxy was just wrong, because the amount of H3 plus you got formed varied. Not surprisingly, in the galactic center, where things are very active, lots of stars, you got more H3 plus formed than on the unfashionable outer wings where we live. And Pete, the astronomers, did not want to believe him. So his papers were rejected, his grant observing time proposals were not funded. Now it's accepted that he was right. But people didn't, that just complicated people's lives too much. They didn't want to know the answer. So it was quite an interesting thing. So that's all in there as well. Anyway, let's move on. This is a picture that did win a Nobel Prize. So this is the first detection of a sort of planet around a standard star made by Meyer and Quelez, Didier Quelez, who was doing his PhD at the time. So it's quite nice to have a PhD project you win a Nobel Prize for. So obviously it was Meyer's idea to look at this. So what they're doing is they're looking at the atomic lines in a star, and the planet orbits the star, and because the center of mass has to be constant, that causes the star just to vibrate just a little, oscillate just a little. So you look at your nice, sharp, accurate atomic lines, and they do this because there's a small Doppler shift in the atomic position of the atomic lines. And that's what you're plotting here. And if you have a very massive planet and a small orbit, then the shift is quite big and the orbit is not very long. You can see this is a 4 point, so it's a slightly funny way, it's 4.23 day period. So 1 year on this planet is 4 days, 4.25 days, which is very convenient for observing. You can get a week's observing time and see nearly 2 years worth of planet. That's one of the problems with trying to detect an Earth clone, because a year takes a year. So if you want to see all this going all the way around, you have to observe for a year, which you can never do because it's always the wrong side of the sun at some time of year. And you can see they've got a really nice convincing sine wave here looking at their data. So as I say, that picture took 24 years, but it won them a Nobel Prize. This is not, the statistics up the top are up to date because I corrected them on Sunday before I came here. But the picture itself is not up to date, but it's correct in the sense that nothing has changed qualitatively. So this is a map of known exoplanets mapped by the astronomical unit, which is the distance of the Earth to the Sun. And if I'm allowed a little rant for a second, you've had a few of them. The AU, capital letters, is the distance of the Earth to the Sun. That changes because over time it's moving by a few millimeters each year. And the Astronomical Union thought it wasn't terribly clever to have a fundamental constant which wasn't constant. So they decided to define the AU as the distance at some particular point in time of the Earth to the Sun. And because they needed to call it something different, they called it the little a, little u. Now I do quantum mechanics, and we work in atomic units. And that's called little a, little u. So these things differ by, I think it's about 10 to the 15 unit of distance, something maybe a bit more. And they have the same name. So that's slightly unfortunate. So I would encourage those of you who are doing distances in quantum mechanics to use Bohr A0 rather than AU, because someone may think you're the distance between the Earth and the Sun, because formally that's what an AU is. Anyway, that's my rant. AU also stands for arbitrary units as well, which get used quite often. So it's an overused expression. So that's the distance scale here. This is relative to mass of Jupiter. So Jupiter lies on the one mass point, Earth lies on the one distance point. And what you can see here is, with the possible exception of Jupiter, you wouldn't detect any of the solar system planets. So if you read somewhere, and I read it quite regularly, that someone has found an Earth-like planet, it's garbage. They haven't. What they have found is planets that may have Earth temperature orbiting cooler stars. So some of these planets in this sort of region here, orbiting things like M-dwarf stars, which are cooler, will be in what's called the habitable zone, will have temperatures of 300, 350 Kelvin. But no one has seen an Earth-like planet going right at a Sun-like star. And actually, with current technology, it's still very difficult to do that. And of course, these planets have orbits of about a month. So again, you could get quite a lot of observations of orbits within 1 year, and it becomes practical. But 1 year per transit of the planet, or per orbit, makes this tough to do. I'm sure it will be done in due course. So we've seen something like 6,000 exoplanets. I've read at least 3 times this year somebody tells me the number we're observing is growing exponentially. That's also rubbish. It grew exponentially while Kepler was flying. So Kepler was a particularly successful planet detection mission run by the Americans, and it went from here like this under Kepler, and then it's gone back to doing this again because Kepler's not flying anymore. So it's going up steadily, but it's not going up exponentially anymore. Right, so that's exoplanets. We have a very biased picture of them. It's much easier to see an exoplanet when it's near its star. So if it's near its star, it's hot. So we've seen some amazingly hot exoplanets. So about 5 years ago, maybe a bit more, Kelt 19b was discovered. Kelt 19b is at 4,000 Kelvin. That's hotter than most of the stars in our galaxy. So M-dwarfs, which are the most common stars, are about 3,000 Kelvin. This thing has liquid iron on it. Everyone thought it was an oddity. Now they've seen about a dozen Kelt 19b type planets. So it may not be the most common form of planet, but it's not a unique planet. So they're really hot, down to hot Jupiter's about 1,000 Kelvin, various other Neptune and Earth-like things. So there's a big tendency for the planets to be quite hot. So that's more important for what I'm going to tell you about why we were doing the calculations than how you do the observations. But anyway, what we want to do, people are out there discovering planets, that's a big activity. But what I'm interested in is actually characterizing planets, what they look like. Obviously, ultimately, you want to know if any of them are inhabited. So we want to know what they're made of, how did they form, what's the weather like. That's another way of saying, do these things vary at all? We're not going to get, at least for a long time, hourly weather forecasts like we have on Earth. and are any of them potentially inhabitable or even inhabited? And the answer to any of these questions is spectroscopy. There's no other way. So we have to actually get spectra of these planets and analyze them. And given we can't see them, that's quite a challenge. So how do you take a spectrum of something you can't actually see? So it turns out that some planets, statistically, it's about 1.5% of them transit when viewed from Earth. So that means, given that we have one particular viewing point in the galaxy, most planets are going to do this, but some of them do this and pass in front of their star when you view from Earth. Now, the 6,000 we know, I think about 2/3 of them transit, and that's non-statistical, and it's because transit has been used as a method of detecting planets, and Kepler in particular, which I said already was incredibly successful, was just doing transit spectroscopy. Sorry, transit detections. So if you do a transit, you've already seen a radial velocity curve. That's not quite such a nice one as the one that won the Nobel Prize, but it's still showing a variation. This thing has a 3.5-day week, so a sort of French working week. And that's star HD 209458. And the convention for naming planets is that the star is implicitly A, though you never give it. And then the first planet out is B, the next planet out is C, and so forth. And I think on that one, we probably won't get a system with more than 25 planets in it. We may do and run off the alphabet, but so far we've, I think, 7 are as big as we got. So from this measurement, you get the period, 3.5 days, and you get the mass. Technically, you get the mass projected in our direction, not their whole mass, but normally they're roughly the same. This is about 70% of Jupiter mass, this particular star. If you do a transit, and I'll show you some, well, this is a transit picture. So this is taking the light from the star, just observing all the light, and then it dips when the planet comes in front and undips again. And that gives you the radius of the planet because it tells you how much starlight gets blocked out. So you get a radius, this thing's a bit bigger than Jupiter, and that gives you a density. And the density gives you some idea of what it's made of. This is basically a ball of hydrogen. But that's all you can get without doing spectroscopy. That's as much as you'll ever know unless you take a spectrum of the planet. So the problem then is, how do you do that? So I told you I'd show you a very bad spectrum. So this was the first detection of a molecule in an exoplanet, and it was made with the Spitzer Space Telescope. It was an infrared telescope launched before anyone even knew exoplanets existed. So it was not designed for doing this. So when I'm saying it was rotten at doing it, that's not a criticism. It was not meant to be doing it. But what you're here is doing is you're looking at a planet as it transits in front of the star at different wavelengths in the infrared, 4 microns, 6 microns, 8 microns, rather broad bands. That's why you've got these widths here. And you're saying how much of the star light gets blocked out. So it's somewhere a bit below 2.5%, 2.45 to 2.35%. If this line is flat, there's no observable atmosphere. It means you basically got something like a hard billiard ball or something, and just light gets absorbed or not absorbed. If there's structure in it, then you must have an atmosphere, because the molecules in the atmosphere are absorbing differentially. So this was enough variation to say there must be an atmosphere here. And my now long-term collaborator, Giovanna Zanetti, appeared at UCL showing this picture and said, well, she wanted to try and fit these observations. And of course, you could be rather speculative about what might be causing them. But she thought it was water and said, I've tried water, but it doesn't quite work. So I said to her after a seminar, this is in 2008, 2007, whose water model are you using? And she told me, and I said, rubbish, use ours. So she used our BT water model, and you got this very nice fit. So we sent this off to Nature, called the tentative detection of water in a extrasolar orbit transiting planet, and Nature accepted it and struck the word tentative off the beginning of the title. So there it is, and luckily it's correct. There were subsequent observations with the Hubble Space Telescope, and here you'll begin to see something which looks much more like a spectrum. So that's one technique, is transit spectroscopy. That was the original technique. So nowadays there are 3 different techniques used, which is transit spectroscopy, cross-correlation Doppler shift spectroscopy, and direct imaging. And I'm just going to go through the pros and cons of each of these. So transit spectroscopy involves you getting several of these different transit curves, basically one for each color. Doppler shift spectroscopy does not look like that. That's a very nice cartoon, and that's just a direct imaging planet. That's not a spectrum. So transit spectroscopy, you have a star, a planet which transits in front of its star, and you should remember if it goes in front, it also goes behind. So actually you get more information than just a transit in front. So you get what's called a secondary eclipse, where the star hides the planet. So at this point, the planet is reflecting starlight back at you. And at this point, it isn't anymore. And it turns out that this primary eclipse tends to give you abundance information on what's in the atmosphere. This tends to give you temperature information. So you get information from the reflections of what the temperature of the atmosphere is. So they're complementary. And you can, though people don't do it very much at the moment, you can look at the whole phase. And then you try to do this for different wavelengths so that you get different transit depths. And that's the information you're trying to get on the star. And the assumption is what you need to know is something you need to know which people didn't know very well. This is actually, this whole area of exoplanets has reinvigorated stellar astrophysics, because we've discovered there are various things we need to know about stars that we don't know very well. One of which is how big they are, because if you want to know how much light you're blocking out, it's the ratio of the radius of the planet to the radius of the star. And if you don't know the radius of the star, you have already one completely unknown bit of data. So that's also important. There's another problem that if you look at this, it could be a star spot. So you have to disentangle transits from star spots, and all sorts of stellar activity becomes very important when you're trying to do this. So there's a whole new area of trying to actually understand how stars behave so that one can understand exoplanets better. But leaving that aside, you get your nice curve here, which in principle shows different transit depths for different colors, and this is actually the same planet as we were talking about and put together by a former postdoc at UCL Angelos. This is what James Webb is doing. When you see James Webb characterizing exoplanets, it's doing transit spectroscopy. This comes from the initial, there was a batch fairly soon after James Webb went up of initial discovery papers, and this was the one they put up on exoplanets. I mean, as you're probably aware, James Webb, 28% of the time is on exoplanets. An awful lot of it is looking very deep into the early history of the universe, which is actually what it was built for. It wasn't built for looking at exoplanets. And this is the spectrum of, I don't like these names. So that's WASP 39b. WASP is a planet detection experiment. There's going to be a detection of some planet around a star which has some completely different name. So HD whatever, that's a standard stellar catalogue number. So that's a perfectly good name, but you have to go onto Wikipedia or somewhere to work out what star that actually is. But anyway, it's WASP 39b, and taken with one of the 2 JWST infrared spectrometers. And you can see that you get, that's the raw data here, you get quite features in here, and then they fitted it to water, CO2, carbon monoxide slightly weakly, and interestingly SO2, that was the first new molecule detected by James Webb. It was detected using a line list computed by a student of mine, Dan Underwood. At least I believe it was, but they weren't polite enough to cite where their data source was. So as far as I know, we're the only hot SO2 line list in the game, so they must have used it. And all the subsequent work is, after I moaned about not being cited, all the subsequent work has indeed cited his work. So there's a new European Space Agency mission, Ariel, which is going to be dedicated to looking at exoplanets. It says 2029 there because I'm not allowed to say anything else, but at the last aerial meeting, it was revealed that it probably won't go up before 2031. But that hasn't been publicly announced yet, so you didn't hear it here first. Unfortunately, that's not true anymore. She's moved across London. She's at King's College London nowadays. But Giovanna Tinetti, who I did the original detection of water with, is PI of Ariel. And the idea of Ariel will be to do about 1,000 transit spectroscopy of about 1,000 exoplanets, going right across the infrared using a single detection. So one of the problems with James Webb is it has several instruments on, and you have to use them sequentially. So if you want to piece together the observations, you can't do them simultaneously. You have to come back and do it again. Ariel will do from 0.5 microns, so the middle of the visible, right the way through the far to the mid-infrared, all in one shot. They're not such high resolution. Giovanna, me, and a gentleman called Marcel Tessigny have founded a company where we're trying to launch a private exoplanet mission, which will be funded by people subscribing to the satellite. And the logic for doing this is we could do this for probably 0.1% of what it costs James Webb, maybe not even that much. So the idea here is, instead of building something completely bespoke, is we use high heritage components, to basically off-the-shelf components, things that have flown in space before, which is what the Earth observation people do. So for instance, we use an Earth observation satellite, we simply point it the other way. And then we use detectors, telescope lenses, all the rest of it that have already flown. We don't spend years and thousands, millions of pounds in R&D. We could launch this in 2027 if we had all the money available to fund it, but we still need to do some more fundraising for it. But we're very much on course to do this. We've got quite a big customer base already who are wanting to do it. And this will be a low Earth orbit satellite. Ariel will go to a Lagrange point outside the atmosphere, which is much more expensive. We already have our first launch coming up next month. And this is a stellar activity satellite. It's a satellite called MOVE, which will go into low Earth orbit. It's going to be launched in November. So it says Q4 there. We have a date which is November the 16th, but that relies on the weather being good in California. So it'll be sometime shortly after November the 15th. I should put a picture of it. That's a mock-up. We have really beautiful pictures of it being built in Hungary. And it's basically sort of this sort of size. And we're going to look at stellar activity, stellar flares, star spots, things like that. So you're going to monitor stars with it to try to build up a picture of how they did it. So we started construction in 2022. We're going to have it in space within 3 years. James Webb was 10 years late, I think, and was originally meant to be constructed in about 10 years. So it took about 20 years. So the idea here is to be quick. We were helped by the fact the European Commission gave us partial funding for this, so that helped things along. And so we don't build anything. We manage them. We sell the data. C3S built the satellite. ISIS Space built the instrumentation. So C3S are in Hungary, and ISIS Space are Dutch in the Netherlands. So transit spectroscopy. So it has advantages and disadvantages. It's good for planets which will be their star. It has broad wavelength coverage is possible, and we'll talk about Ariel doing pretty much across the infrared and most of the visible all in one shot. You get complementary information from primary and secondary transit. In principle, it gives full information, though there's a lot of interpretation needs to be done for that, and I'll come to that in a second. However, rather obviously, the planet must transit when seen from Earth. And that's 1.5% of all planets. There's a lot of the ones we see at the moment. And there's an American mission called TESS out at the moment, just beginning to release data. That's also doing transit detection, so there will be more. And in fact, the European Space Agency is going to launch a mission called Plato, which is rather like Kepler, so that will do more. So there are lots of transiting planets known. Largely requires space observations. I mean, in principle, you could transit spectroscopy from Earth, but I've never seen anyone really attempt it. Going to space is expensive, so that limits the amount of data you can have. Interpretation can be rather model dependent. I don't know anyone else who's been following the arguments over K218b, which is another James Webb observation, but you could say the interpretations vary rather wildly on a rather sparse set of data, I think would be a polite way of putting it, so that they are dependent on what you assume in your models to fit the data. And because you get relatively little data and planet atmospheres are potentially very complicated, there's rather a lot of freedom of how you choose your parameters in the model, and then you get different results. There's a real problem with this for looking at Earth. I mean, our atmosphere is a few hundred kilometers. You're looking for variations in atmospheric height with absorbance, things like water or CO2 or other molecules that may be in the atmosphere. And those variations are going to be relatively small, so that you're given against the whole radius of the planet. You basically need transit spectroscopy to do at least one order of magnitude more than it's doing at the moment to get a spectrum from an Earth-like planet. I think it's possible, but it's not possible at the moment with current technology. Typically, the resolving power is below 3000. I don't think that's intrinsic, but James Webb maximum resolving power is 3000. In practice, all the spectra I've seen aren't even at 3000 because you don't get enough photons, so they bin the resolution down to somewhere between 300 and 1000 just to make sure they get enough data. So to analyze this, what you need to do, classic inverse problem, you need to make a whole atmospheric model, and then you radio transport through the atmospheric model and you match it to the experiment, the observation. You can't go from the observation to an answer. You have to make a model, and then from the model, go to the observation. So the locals at UCL have a model called Tau Rex, which is very good, but there are probably 10 to 12 other models out there. They all use our data, XML, which I said I'll talk about tomorrow. So that's actually what you do, is you build a model based on your line lists and atomic lines and all the rest of it, and you see where that fits the experiment. And if you go back to that's exactly what they were doing here. So I suspect they didn't cite any molecules here, but all these molecules are in XML, so I suspect they just took the XML data. But for the other three, water, CO2, and CO, there are other sources. I would say not as good, but and I'm biased. Actually, it's not true. Our CO2 is not that wonderful. Okay, so cross-correlation or high-resolution Doppler shift spectroscopy. So this is completely different, and I think very elegant. So what they do here is you do it from the ground, is you look at the whole orbit of a planet. It doesn't have to transit, but you need to be able to see the orbit. And of course, as it's orbiting, it has a different Doppler shift relative to its star. So if you could see the lines, this is a cartoon, this is not real data. You'll see real data in a minute. If you could see the lines, they would do this because of the Doppler shift. This is not real data in more senses than one. These are the model up telluric lines. They tend to be much worse than this. You tend to get whole chunks which are blocked out by Earth-like lines. But the point is that the lines in the Earth obviously don't shift as the planet moves around the star. So you can blank them out, and then you can look for the bits of the shift. That doesn't solve the problem, because you still basically start off with white noise. I'll go on to the next transparency. You start off with data which you can't see anything at all in. And what you actually say is not looking for one line. You say, we want water. Water has 500 lines in the region we're looking at. We make a phase mask with all my water lines, and then we move it around the planet like this, and we see if it correlates. So you have to look for the whole spectrum all in one go. What you end up was, and these diagonal things, I'll show you another picture that explains these diagonal things show that there's a correlation there with what's going on. I'll show you a picture explaining that correlation. And this was actually invented by a guy called Ignaz Snellen, who certainly has, if not won a Nobel Prize, he won a very fancy Dutch prize, which is valued about 3 times as much as the Nobel Prize for doing this. And it's I think it's a very neat idea. So this is what a detection looks like. So what you cross-correlate is obviously you've got a Doppler shift of the whole system, because the star is Doppler shifting from Earth, and the planet is Doppler shifting around the star. So you don't know because this now has to be extremely precise, you tend not to know to a few kilometers per second what the star is Doppler shifting by. So you cross-correlate the Doppler shift of the star with the Doppler shift of the planet with your phase mask, it's called, your lines. And when it works, you get a diagonal feature like that. And that gives you detection. So this was given much the strongest detections for molecular features. So it gives you detections that can be between 5 and 10 sigma. And if you remember when the discovery of the Higgs boson was made, 5 sigma was considered the minimum detection limit they would count on. Most of these transit spectroscopy detections are more at the 2-3 sigma level. It's lump and bump spectroscopy. These are really quite strong detections. This is not Mahatma Gandhi, this is Sid Gandhi, who's at Warwick University in the UK, who's one of the people who does this sort of work. He is Indian by birth. Sorry, I've turned this off if I done. How am I doing for time, by the way? Sorry? Okay, well, I'll give you, I think, probably, yeah. Shall I finish this bit? Then maybe we'll start, we'll cut slightly this afternoon, so it's nice to just finish the section. So this method has a lot of advantages to it. It provides really firm detections greater than 5 sigma. You can do ground-based observations, and indeed people are building 30-meter telescopes to do exactly this. So things like the ELT, European Extra Large Telescope, the VLT, the Very Large Telescope, are being built precisely because they want to do this sort of spectroscopy. Telluric effects can be removed, and it doesn't rely on the planet transiting. So that's all very positive. It requires very high-resolution telescopes. That is a negative, but it's not a showstopper. You sort of think you could do this for anything, but you can't actually, because if the planet moves too slowly, you don't get a Doppler shift. So if the planet is a long way from the star, even though that means it's less likely to transit, you can't really do this either because it's not moving fast enough to give a serious Doppler shift. So it has a sort of commonality with the planets you can see using transits. Because you've used all your data just to make a detection, you don't really get other information. You don't get abundance information. You don't get temperature information. People who do this tell me they think they have methods they can work it out from. They can get abundances and temperature effects. But so far, it's basically just been detections. So you said, there is HCN in this planet, or there is water in this planet. It doesn't tell you how much. It doesn't tell you how hot the planet is. And there does seem to be a problem with false positives. So there's a slight issue that actually people are saying, oh, I've got a definite detection at 4.5 sigma. And you try another observation, another set of data, and there's nothing there. So that's a technical issue people don't seem to have sorted out. It's like the transit spectroscopy model dependent. Very quickly, direct imaging. In principle, what we want to do, in practice, 6 planets you can look at it, 7 planets you can look at it, because basically, you have to be able to separate the planet from its star, and that's only possible if you have high angular separations. That means, firstly, the planet has to be a long way from the star, and perhaps even more important, the star has to be very close to Earth. If you're the other side of the galaxy, it doesn't matter how far. This is an example of a planetary system where you've got the star there and 3 planets, which are... Oh no, sorry, you've got B off here. So B, C, D, so you've got 4 planets. And what you do is you use, which used to be called a coronagraph, because you can see the solar corona if you put it on a telescope, and if you're aware an eclipse of the moon behaves like a fabulous coronagraph because the moon happens just to fit exactly, so it blocks out the sun. Nowadays they're calling them star shades, because obviously we're not trying to get rid of the solar corona, we're trying to get rid of the starlight. But you put that in front of the star to try and block out what you're seeing. And James Webb has done at least one detection with this method, and I don't have a chronograph. They must have done it in software after taking the observations. and the Americans are due to launch something which is called the Nancy Grace Roman telescope. In my view, has the worst logo ever, but I got told off for saying that by an instrumentalist who liked having their instrument featured in the logo, but I think it's not very interesting. And this is going to have a chronograph on it, so hopefully we will see some more spectroscopy. In the slightly strange geopolitics of the world, the Americans are very into direct imaging. The Europeans are very into transit spectroscopy and in particular cross-correlation spectroscopy. I think both are into transit spectroscopy. The Europeans tend to be into cross-correlation spectroscopy. And I think, oh yes, so it's straightforward. This is just a straight observation, so it's much more straightforward to interpret. And what you see now is something completely different from what you're seeing the others. So these, normally a planet which is very far from its star, if you think of Pluto, it's very cold. So you wouldn't see anything because it doesn't radiate. But if you're in a very young planet, you're still contracting under gravity and you're glowing. So this method allows you to see planets at the point they're being formed. So basically less than 20 million years old. And then they glow, and then you get a completely different aspect to the mature planets you're looking at transiting in the other spectra. So that's quite interesting. It's complementary. But the angular resolution must be good so you can separate the star from the planet. There are very few candidates, I said about 6. So it can't be used for the vast majority of exoplanets. So let's start there tomorrow. Okay, so thank you very much, and I'll see you all at 2:30.